Hey guys, so today I'm going to walk you through the independent events tutorial. Just like always, we're going to skip through these first couple slides because they're just kind of the name and the objective. And so here's this introduction, and what this all talks about. You're free to read it on your own. You can pause and read. This is talking about how probability and statistics are used in insurance a lot. And this is something called actuarial science. And so if you're really, really good at math and you wanted a job that involved a lot of math, then one thing you could do is become an actuary. And they work with insurance companies and try to figure out how to make sure that the insurance companies are profitable. So they try to figure out how much they have to charge based on all the probabilities of certain events happening. So we have this knowledge article, just like they always do. I'm going to open it. And this talks about life tables, which is kind of hard to understand when you're just kind of reading it. So we're just going to kind of go with the flow as we go along here. And so on our next slide, this is going to be an activity, and we're going to look at a life table. So we are going to click on this and take us to a big long document here from the CDC, which you guys have been hearing lots about the CDC lately. And we want to look at, if you look, we want to look at table 1. Okay, so we're going to just scroll down. That's table A, so we don't want that. This is 61 pages. Oh boy. I believe it starts on page 8. Yes, so this is table 1. So what this is a life table, and this says, it has all kinds of information on here. Okay. This first column, the first column is the age, so between 0 and 1, 1 and 2, so on. And it gives the probability of dying if you're between 0 and 1, and then 1 and 2. This is the number surviving to age X, so it's always, the tables start with 100,000, and then like if you look here, 99,324 people survive to age of 1. Number dying between that, so that means there's 46 people dying between ages 1 and 2. We're going to kind of skip over these two columns here, and then here, the expectation of life. This is how many years left you have. So if you're between 0 and 1, you'd be expected to have 77.9 years left. Okay, so that's the life table. So let's look at this. What is the probability of dying between ages of 70 and 71? So we're going to come over here to 70 and 71. Okay, the probability of dying between 70 and 71 is this number right here, 0.020424. 0.020424. And remember, on these activities, we are able to check our answers. And yay, we got it right. Okay. How many people out of 100,000 will survive until age 90? So we're going to go back here, and now we're going to look at 90. Okay. And I want to go to the number surviving to that age, which is 21,526. So let me put that in here, 21,526. And we check our answers, and we got it right. Okay, so really what we're doing here is we're just trying to figure out how to read this table because we're going to need it later on. Question 3. How many people out of every 100,000 would die between ages 99 and 100? So if we come over here, it's the third column, or I guess that's the fourth column. And 795 people would die between ages 99 and 100. So that's what we're going to put in here. Submit. Yay. Okay. How many more years can a 75-year-old person expect to live? We go back to up here to 75, and all the way down at the end, it looks like a 75-year-old could expect to live 11.7 years more. Okay, that's good. Okay, self-evaluation, we give me a 5. I think we did a great job. And then, so that activity was really just about, can we read a table? Okay. And this here explains, these are the headings of the table. The first column gives you the age ranges. The second one, Q sub X, gives the probability of dying between the ages. And this is saying, I kind of said what all of these were here. These two rows right here, person years, we don't need that for today. They do have a use in actuarial science, but we're not quite there yet. So you're never going to use the columns that say person years. All right, based on the table in data, based on the data given in table 1, how many people out of 100,000 will survive till the age of 85? So let's go to 85. So how many people out of 100,000 will survive that? And that's 38,565. So let's click that, and we got it right. So that's just some more practice with making sure we can get answers from the table. So now we're going to talk about independent events. So this is just kind of saying, hey, we got these applications for life insurance policies for 2 different infants. We're going to look at this activity and do some work. We're still working with that same life table. The 2 infants that we have gotten applications for are Carl and Susan. And so we're going to look at question 1, which says, compute the probability of the infant Carl turning 44 years old. So if you want to use probability notation, say the probability of A, or you can even write it out. Those are the same thing. So start with A, the probability of Carl turning 44 years old. Well, we're going to come over to our table, go to 44. That is going to be, now this right here says 0.002629. Now if you look here, this is the probability of dying. So that is not what we want, okay? But we can't just do 1 minus that. So let's come over here. Let's do the number surviving to the age of 44. So if I look at this, from that table, it says that there are 95,726 people that will survive until the age of 44 out of 100,000. Okay, so to figure out what that probability is, we're going to divide by that original number, which is 100,000. Now, if you use your handy dandy calculator and work that out, you will get 0.95726 as the probability of Carl turning 40 years of age. Okay. And we also want to find the probability of Susan turning 44. Now, it's actually going to be the same exact thing, because using the life table, we're going to look at the same number. So this is also the probability of B, which is Susan turning 44 years old. Okay, and good. If we just double check that, we're good. Okay. Next, hold on 1 second. Okay. Now in question 2, we want to compute the probability of Carl turning 44 years old, given that Susan has turned 44. So this will be the probability of A given B. It's actually something different. Okay. Now, the thing to keep in mind here is that Carl's age has nothing to do with Susan's age. Like they are independent events. So because they are independent events, they have no bearing on each other. So that means the probability of Carl turning turning 44, given that Susan has turned 44, is just the original probability, which is going to be 0.95726. Okay, so because they're independent, we just take the original probability, which is right. And then now on question 3, it's asking for the probability of B given A, of Susan turning 44, given that Carl has turned 44. But again, they are independent. So it will just be the original probability that we gave for Susan turning 44, which is 0.95726. Okay. Okay, so now this one is asking something a little bit different. This is saying, what is the probability of both Carl turning 44 and Susan turning 44? So that is A and B. Now, if you think back a couple lessons, whenever you have independent events, the probability of both of them happening is the same thing as the probability, the individual probabilities being multiplied together. So this would be 0.95726 times 0.95726. If you use your handy dandy calculator and work that out, this is what you would get, 0.91634. You're going to multiply the two together. And you can only do that if it's an and season and independent events. We have the self-evaluation, but we're going to move on. Okay? So this is basically just a summary page. These are some important formulas. Maybe you want to write those down. But again, this is only for independent events. What we're going to look at. Well, first I think we have a problem. Yes. So the probability that Shelly will go to a movie event A on Friday is 0.78, and the probability that Danielle will go at B is 0.63. The probability that both Shelly and Danielle will go is 0.4914. So we want to figure out which one is true. Now this 0.94914, that is the probability of both happening. So I'm going to take my calculator and I'm just going to multiply 0.78 times 0.63 and see what happens. I get 0.4914. Now I multiplied the individual probabilities and got the probabilities that both of them will go. So that means the events are independent. I'm going to rule out these last two. And it's going to be this option right here. They are independent because when you multiply the individual probabilities, you get the compound probability. Okay. And that's for independent events. Of course, we got to talk about dependent events. Those are ones that do influence each other. Like here, smoking and drinking can drastically lower life expectancy. So if you're going to get a life insurance policy, they're going to ask you, do you smoke, do you drink, and take that into effect. So this activity that we're going to look at, we're still looking at table 1 in the life table. I want to find the probability of infant Susan turning 44 years old. Okay. Now this is that same probability we did before in the last one, so I'm just going to use that same number, 95726. But remember what we did is we looked at 44, and we saw how many people lived to that age, and we divided by the original amount, which is 100,000. Okay. And then what is the probability of infant Susan turning 45 years old? Well, we look at the 45 column. It's 95,475. So we're going to do 95,475 divided by 100,000. And that is going to equal 0.95475. And that's the probability of Susan turning 45 years old. Now we're going to look at some mixtures here. What is the probability of Susan turning 45 years old given that she has just turned 40? I'm sorry, I read that wrong. What's the probability of Susan turning 44 years old given that she has just turned 45? Well, think about it. If you turned 45, well then haven't you already by default made it past 44? So in this case, the probability is going to be 1. Okay, because if you just turned 45, that means you have absolutely already turned 44. Okay, so in this case, it's 1. Now notice that the probability of A given B, we don't multiply the individual probabilities. That's because they're dependent. Because you cannot turn 45 unless you have already turned 44. Now the other way, what is the probability of Susan turning 45 years old given that she has just turned 44? So if we look at this one, these are again dependent events. So what I need to do is I'm going to look at the probability of dying between 44 and 45. Okay, so if I come over here, the probability of dying between 44 and 45 is 0.002629. 0.002629. Okay, so that means if you made it to that 44th birthday, that's the probability that you're going to die in the next year. Which means if I take 1 minus that number, that's going to be the probability of not dying during that year. And again, your handy dandy calculator will work that out. 0.997371. And that is going to be our answer. So that's a little bit different because if you make it to your 45th birthday, that's the 44th birthday, that doesn't guarantee you're going to make it to the 45th. Okay, but if we can figure out the percentage of people that are going to die, that means if we subtract it from 1, we can get the probability that you won't die. All right, and then finally, question 5, what is the probability of infant Susan turning 44 and also turning 45? So this is really asking like the probability of A and B. And these are not independent events, so I can't just take the individual probabilities and multiply them together. But the thing to recognize here really is going to be just the probability of turning 45. Because in order to make sure both of them happen, you just look at that probability of turning 45, which is something that we had already calculated up above here. Okay. But again, they're not independent, so I cannot multiply them together. Moving on. The general probability that Ashley parks her car in a no parking zone, event A, is 0.34. The general probability that she gets a parking ticket is 0.22. The probability of her parking her car in a no parking zone and getting a parking ticket is 0.22, given this information, which is true. So again, if you have the two individual probabilities and the probability of them both happening, you want to multiply them together to see if they're independent or dependent. And when I do 0.34 times 0.22, I get 0.0748, which means that they are not independent. They are definitely dependent. And the reason I know that is because their probabilities, the individual probabilities, do not multiply to the compound probability. So here's another summary. This is for dependent events, so you could write that down or take a screenshot of that. One more activity. All right, but now we're going to use something different. We're going to use tables 2 and 3 in the life tables. Here's table 1. Table 2, you'll notice, is the life table just for males. Table 3 is for females. Okay. So based on this information in table 2, how many males from a randomly selected population of 100,000 males live to the age of 44? So I'm going to go to the male table, go to 44. How many? Well, that's going to be 94,533. And then if I look at that, how many live to be 85? So we're still looking at males, so I'm going to look at the 85. 31,177. We're getting that from our table. Okay, so considering that Carl is 44 years old already, what's the probability that he will live to the age of 85? Well, so the number of people living to the age of 85 is 31,117. Now, I'm not asking just for the probability of living to 85. If I was, I would divide by the original number of 100,000. But here, given that he's already 44, that means I want to divide by the number of people who live to 44, which is at 94,533. Okay. So again, this is a nice problem to put in your calculator. You get 0.3298 for the probability. Okay, so because we know he's already 44, we know he's part of that 94,533. Now, based on this table, how many females live to be the age of 38? So we'll go to the female table. 38 is right here. That's 97,825. And then how many live to be 85? So let's look here for 85. 45,436. And then considering that she's 38 years old, what's the probability that she lives to 85? So again, the number of people living to 85, number of women, is at 45,000. And if I just wanted just the probability of living to 85, I'd divide by 100,000. But since she is already 38, I'm going to take that 97,000. And when I work that out in my calculator, I get 0.4644. So that's the probability that if you're already 38, that you're going to live to 85. Yay! Probability of Carl turning 85 given that Susan has turned 85. Those don't have any bearing on each other. So I could say that the probability, I'm asking you the probability of A given B, but because they don't influence each other, that really just means the probability of A. So the probability of Carl turning 85, if we scroll up here, we already figured that out. We know he's 44 right now, so this is that probability that he's going to turn 85, which is 0.3298. Which if we look at the answer, that is correct. Okay, now 8's asking the opposite. What's the probability of Susan turning 85? Given that Carl has turned 85, so this is what it's asking, but they are independent events, so they have no bearing on each other. So it'll be just the probability of B, which we figured out Susan was already 38, so this is her probability of making it to 85. And let's double check our answer. Good. What's the probability of both of them turning 85? Well, in that case, those are independent, so you're going to multiply the individual probabilities together. So the answer is from number 7, and the answer from number 8. And if you use your calculator, it's 0.1531. Okay. All right, we are almost done with this. I know this is getting long. Here's a summary. Here are independent events. Here I have the probability of 2 individual events and the probability of them both happening. Are they independent or dependent? So what you do is you take your calculator, you do 0.73 times 0.45 and see if you get 0.3285, which you do, which means that they are independent. Okay? Here's a summary that you can look at. Here's our gold star for finishing it. And you guys are all done. All right, let me know if you have any questions.